Hi, this is Srija. I'm from CSDC section department. Today I'm discussing about the rank factorization in matrices. So we discuss about the definition. Let A be an M cross N matrix. Then the column space of A is C of A is C of A is to AX is to X belongs to Fn, and the row space of A is R of A, that is YTA is equal is to Y belongs to Fn. We call dim R of A the row rank of A and dim C of A the column rank of A. We refer to a basis of C of A consisting of columns of A as a column basis. A row basis is defined similarly. If A has column rank R, then any R linearly independent columns of A form a basis for C of A. Every maximum linearly independent set of columns of A contains exactly R vectors. Any R columns of A which generate C of A form a basis of C of A. Now we discuss about one theorem. For any matrix A, the row rank of A equals the column rank of A. Definition: the rank of a matrix A is the common value of the row rank of A, and the column rank of A is denoted by P of A. Definition: M cross N matrix A is said to be of full row rank if its rows are linearly independent, that is, if its rank is M. Similarly, A is said to be full column rank if its columns are linearly independent. A left inverse of a matrix A is any matrix B such that BA is equals to I. A right inverse of A is any matrix C such that AC is equals to I. A matrix B is said to be an inverse of A if it is both a left inverse and a right inverse of A. So we discuss a theorem. Let A be a M cross N matrix over F. Then the following statements are equivalent. 1. A has a right inverse 2xa is equals to 0. Then x is equals to 0. The third statement is A is of full row rank. And the another theorem is let A be a M cross N matrix over F. Then the following statements are equivalent. First statement is A has a left inverse, and the second statement is AX is equals to 0. Then x is equals to 0. The third statement is A is of full column rank. I hope you understood about these two theorems. So we enter into our next slide. So we discuss about one more theorem, one more definition. Let A be M cross N matrix with rank R greater than or equal to 1. Then P comma Q is said to be a rank factorization of A if P is of order M cross R, Q is of order N cross N, and A is equals to PQ. Now theorem: every non-null matrix has a rank factorization. Proof: let A be a M cross N matrix with R. Let B is equals to x1 is to x2 up to so on xr be an M cross R matrix whose columns form a basis of C of A. Then for each j is equals to 1 comma 2 up to so on n, each column of A comma A into J is a linear combination of the columns of B. So there exists an R cross 1 vector Yj such that A into J is equals to Byj. Now A is equals to A into 1 up to so on A into n, and By1 is to Byn, where in this we are taking B as common. B into y1 up to so on yn is equals to bc, where c is equals to y1 is to up to so on yn. A null matrix cannot have a rank factorization since there cannot be a matrix with 0 rows. Rank factorization of a matrix is not unique. The choice of the matrix B is not unique because the columns of B are coming from the column basis of A. If B, C is a rank factorization of A, then CT, BT is a rank factorization of AT. When a factorization is a rank factorization, we have a question here. For that we have a theorem. So let's discuss about the theorem. Let A is equals to PQ, where P is a M cross K matrix and Q a K cross N matrix. Then the rank of A is at most K. Moreover, the following are equivalent. The rank of A is K. P, Q is a rank factorization of A, where P is of full column rank and Q is of full row rank. The columns of P form a basis of C of A. The row of Q form a basis of R of A. Now, let's discuss about corollary. If P, Q is a rank factorization of A, then C of P is equals to C of A, R of Q is equals to R of A, and N of Q is equals to N of B. For the corollary, we discuss some theorems and the proofs. Theorem is, if A is equals to A squared, then rank of A equals trace of A. For that, proof is, the result is trivial if the rank R of A is 0. So let R greater than or equal to 1. Let P, Q be a rank factorization of A. Then PQ is equals to PQ is equals to PI RQ, since P is of full column rank and of full row rank. Left hand cancellation laws are applied. We get PA is equals to IR. Hence rank of A is equals to R is equals to trace of IR is equals to trace of QR is equals to trace of PQ is equals to trace of A. Finding a rank factorization of a matrix A of rank R is easy when A is represented in the following nice form. The theorem is, let A be an M cross N matrix of rank R greater than or equal to 1. Then there exist permutation matrices P and Q such that A is equals to P. The matrix is B, BC, DB, DBC into Q, where B is non-singular matrix of order R and C and D are some matrices of order R cross N minus R and M minus R cross R respectively. When a matrix A in the above form can be factorized as A is equals to P1 Q1, where P1 is equals to PB DB and Q1 is equals to IR is to C, Q. Since P1 is of order M cross R, it follows that P1, Q1 is a rank factorization of A. Now let's discuss about rank. Let C denote the field of complex numbers and C, Xn the collection of Rn by n. Matrices with entries from C, if A, E, X double dash 71x, let A denote the conjugate transpose. Sometimes it's also called the Hermitian adjoint of A. A is formed by taking the complex conjugate of each entry in A and then transposing the resulting matrix. A very important but not always easily discoverable non-negative integer is associated with each matrix A in C double dash X. The rows of A can be viewed as vectors in C dash 1 and the columns as vectors in C triple dash 7. The row span a subspace called the row space of A. The dimensions of the row space is called the row rank of A. Now, for A is EC 71 into I R of A less than minimum n comma n. For A comma B C X I R of A plus B less than R of A plus R of B. For A EEC NXRT R of A is equals to R of A is equals to R of A into A. For AE, C is 7 IX 0.7 and BE CXP, comma R A or AB less than minimum of R of A, comma R of B. If B and C are invertible, then R of AB is equals to R of A is equals to R of CA. Full rank factorizations. Let AECM in is to 7 cross n with R greater than 0. If we can find F in C 7 cross R and G in C minus xn such that A is equals to FG, then we say that we have a full rank factorization of A. It is not difficult to see that every matrix A in C triple dash XU with R greater than 0 has such a factorization. One approach. To choose for F any matrix whose columns form a basis for the column space of A, then since each column of A is uniquely expressible as a linear combination of the columns of F, the coefficients in the linear combinations determine a unique matrix G in CRX double dash I with A is equals to FG. Moreover, R is equals to R of A is equals to R of FG less than R of G less than R, so that G is in C cross N. Another approach which will lead us to an algorithm is to apply elementary matrices on the left of A, that is elementary row operations, to produce a unique row reduced echelon form of A, RREF into A. In other words, we compute an invertible matrix R in C M cross N with RA is equals to Z R cross N by 0 or O M minus R cross N. So we have some examples here. Those are the two, they given the two matrices A and B, where A is equals to, it is a 4 by 4 matrix, 1 3 1 4 2 7 3 9 1 5 3 1 1 2 0 8, and the B is also 4 by 4 matrix containing elements 1 0 minus 2 0 0 1 1 0 0 0 0 1 0 0 0 0, and the B is in the reduced echelon form of A. Then C is obtained by removing the third column of A, the only one which is not a pivot column, and F by getting rid of the last row of zeros from B, so that we are getting C as, by removing the third column of A, we are getting C as 1 3 4 2 7 9 1 5 1 1 2 8, and by removing the fourth row of B, we are getting F as 1 0 minus 2 0 0 1 1 0 0 0 0 1. So it is straightforward to check that A is equals to 1 3 1 4 2 7 3 9 1 5 3 1 1 2 0 8 is equals to 1 3 4 2 7 9 1 5 1 1 2 8 into 1 0 minus 2 0 0 1 1 0 0 0 0 1, that is CF. Now we discuss about one proof. Let P be an n cross n permutation matrix such that AP is equals to C comma D in block partitionated form, where the columns of C are the R pivot columns of A. Every column of D is a linear combination of the columns of C. So there is a matrix G such that D is equals to CG, where the columns of G contain the coefficient of each of those linear combinations. So AP is equals to C comma CG is equals to C into IR comma G, IR being the R cross R identify matrix. We will show now that IR comma G is equals to FP. Transforming A into its reduced row echelon form, B amounts to left multiplying by a matrix E, which is product of elementary matrices. So EAP is equals to BP is equals to ECIR comma G, where EC is equals to, it is a 1 by 1 matrix IR and 0 in the column. Then we then can write BP is equals to, it is a 2 by 2 matrix IR 0 0 IRG 0 0, which allows us to identify IR comma G is equals to FP, that is the non-zero R rows of the reduced echelon form with the same permutation on the columns as we did for A. We thus have AP is equals to CFP, and since P is invertible, this implies A is equals to CF, and the proof is completed. Rank of A is equals to rank of A transpose. An immediate consequence of rank factorization in that the rank of A is equal to the rank of its transpose, A transpose. Since the columns of A are the rows of A transpose, the column rank of A equals its row rank. Now we see a proof. To see why this is true, let us first define rank to mean column rank. Since A is equals to CF, it follows that A transpose is equals to F transpose C transpose from the definition of matrix multiplication. This means that each column of A transpose is a linearly combination of the columns of F transpose. Therefore, the column space of A transpose is contained within the column space of F transpose, and hence rank of A transpose is less than or equal to rank of F transpose. Now F transpose is n cross R, so there are R columns in F transpose, and hence rank of A transpose less than or equal to R is equals to rank of A. This proves that rank of A transpose less than or equal to rank of A. Now apply the result to A transpose to obtain the reverse inequality. Since A transpose whole transpose is equal to A, we can write rank of A is equals to rank of A transpose whole transpose less than or equal to rank of A transpose. This proves rank of A less than or equal to rank of A transpose. We have therefore proved rank of A transpose less than or equal to rank of A, and rank of A less than or equal to rank of A transpose. So rank of A is equals to rank of A transpose. Now we have some attempted solutions. 1, 2. First one is, since the rank of A is K and A belongs to R n cross n with rank 1 less than or equal to K less than n, then clearly our rank of A cannot be n, hence A is not invertible, which implies that the full rank factorization of A is not unique. Now the attempted solution 2 is, we need to find the span of the columns of A. Consider a non-singular matrix M belongs to R k cross k, then we have A is equals to xy whole transpose is equals to xmm minus 1 y transpose is equals to xm ym minus transpose to the whole transpose is equals to xy transpose. For x belongs to R to the power n, consider Ax is equals to xy transpose x is equals to xv. Since y u as rank k, so is y transpose, and therefore for any d belongs to R to the power of k, there exists at least one x belongs to Rn such that d is equals to y transpose x. Then as a result, R of A is equals to R of x. So we have attempted solution 3 also. So full rank factorization in echelon form. In this section, we derive a necessary and sufficient condition for a matrix to have full rank decomposition in echelon form. Moreover, we prove that if the full rank factorization in echelon form exists, then it is unique. We have theorems and the proofs. So let's discuss about one theorem. Let A belongs to Rn cross M be a matrix with rank of A is equals to R less than or equal to minimum n comma m. Then A admits a full rank factorization in echelon form if and only if the upper echelon form of the first R linearly independent rows of A can be obtained with no pivoting. So we see the proof also. Let A1 belongs to R cross M be the matrix formed by the R first linearly independent rows of A. Then there exists a unique reduced lower echelon matrix F1 belongs to Rn cross R such that E is equals to F1 A1. Suppose A1 is transformed to an upper echelon form with no pivoting, so there exists a unique factorization L1 D1 U1 where L1 belongs to R cross R is a unit lower triangular matrix, D1 belongs to R cross R is a non-singular diagonal matrix, and U1 belongs to R cross M is an upper echelon matrix with a rank of U is equals to R. Therefore, A is equals to F1 into L1 D1 U1 is equals to F1 L1 into D1 U1 is equals to LDU. So this is also the proof, continuation proof. So with this, I hope you understand about this session. And with this, thank you. I'll end this session.